Okay, hello, this is going to be chapter 15. Again, this is for Chem 40B. Chapter 15 is a bit of a rough one. There's a lot to cover in this. So I will split this up into two videos. You're watching the first one now. And this is chapter 15's title is Benzene and Aromaticity. We'll get into what aromaticity means, but you have seen before what benzenes are. And they're these rings right here, right? That you can draw them in two separate forms, but they are a cyclohexane with double bonds every other carbon. So we would call that a benzene ring. And these carbons are conjugated and allylic to each other, right? Conjugated and allylic from the last chapter. And there's actually resonance here where the double bonds can move adjacent to one another. So like this. And then if they move, this double bond here goes up here, which is denoted right here. This double bond from the bottom goes actually to the bottom. And then this double bond from the top right goes up to the top left, right? And because of this, each carbon here, each of these carbons are participating in a double bond. And that means that the electrons are completely delocalized, and you have, although it seems like there are 3 pi bonds here, there are actually 6 pi electrons because of the cyclohexane. There's 6 of them, right? So 1, 2, 3, 4, 5, 6. And because of the resonance and how each double bond can be moved by resonance, we would call this compound, it would be an aromatic. It's an aromatic molecule. Okay, so let's go into some of the chemical properties of aromatic molecules. Because of their pi bonds, they're usually nucleophilic, right? So you've seen this in alkynes and alkenes. The only way they can be nucleophilic is if there is a very strong um, haloalkane bond, right, with like either H to Br or HF. That bond is very electrophilic because hydrogen has a large um, delta positive, and then the double bonds, even though they're really weakly nucleophilic, they can still attack. Okay, so they are nucleophilic, and aromatic systems are very, very stable. They're one of the most stable systems, even more stable than like a tertiary carbocation or a tertiary radical, because of the fact that they each have pi electrons, and those pi electrons contribute their electrons to the system. Okay, so they're very stable, to the point where if you react it with something, they're most likely going to keep, and they want to keep what makes them aromatic. Okay, so let's actually see what makes a molecule aromatic. There are a couple of prerequisites that you have to look at to see if a molecule is aromatic. Okay, so the first one is the number of pi electrons, right? As we seen at the top here, it has 6 pi electrons. So the number of pi electrons has to fit this 4n plus 2. Okay, so let's say you have 6 pi electrons, right? Can you satisfy 4n plus 2, where n is any integer? So if you plug in n is equal to 1, you have 4 times 1 plus 2, which is equal to 6, right? But if you have 4 pi electrons, you can't put 1 because 1 would be 6. You can't put 2 because if you put 4 times 2, it'd be 8 plus 2 is 10. And then if you put 0, it would be 4 times 0 plus 2, which is 2. So 4 does not cut it, okay? So this is called Huckel's rule. It's a very famous, I think that's how you spell it, I don't know, with the two, Huckel's rule, okay? And then the pi systems have to be cyclic, which means all atoms in the ring must be involved in the pi system. And you see that up here, where each of the atoms have their own pi electrons, which means that it fits that rule. And then the third one is the molecule must be on the same plane. And what I mean by this is each molecule either has to be sp2 or sp. It can't be sp3 because sp3 is a tetrahedral geometry, right? Or anything that is sort of like that, where sp2 is trigonal planar, right? So they're in the same plane. And then we can take a look at this example right here. So let's take a look at this carbon here. It has 1, 2, 3, 4. This hydrogen has 1, 2, 3, 4. So it has 4, which is good. It has 3 elements, so it's sp2. And then let's take a look at this carbon. This carbon is the same. It's also sp2. This carbon is the same, sp2. This one is sp2. This one is sp2. And then this one is sp2. You see how they're all sp2 hybridized, which means that they are all in the same plane, right? Okay. And then the last one is they have to have conjugated pi bonds. Conjugated pi bonds just means pi bonds that are one carbon away. You see how these, if you go one carbon away, there's another pi bond here, right? So that means these are conjugated. One carbon away, there's a pi bond there, right? So we'll get into some examples coming up shortly, okay? So now that you know the rules and what makes a molecule aromatic, let's see some examples. We have a lot of examples here, okay? So let's take a look at this. Remember your rules. It has to satisfy. Well, first let's see if they're all within the same plane, okay? So this carbon is sp2, good. This one is also sp2. We're off to a good start. This one is sp2 as well. This one is sp2 as well. But what about this one? This one has 2 hydrogens here, right? It has 1, 2, 3, 4. It has 4 elements, so it's sp3. Because of that, it's not in the same plane. Therefore, it is not aromatic, right? Not aromatic. And it also breaks a couple of rules as well, where if you remember Huckel's rule, where it has to satisfy 4n plus 2, right? 4n plus 2. How many pi electrons does this molecule have here? It has 2 pi bonds, right? Which means it has 4 pi electrons. And is there a number? Is there a whole number that can fit this n? No, I don't see any. If I put 0, it's 2. If I put 1, it's 6. So it also breaks that rule. And also the fact that it's not conjugated, right? This is conjugated, sure, but there's no double bond here. So you only needed to add this double bond here, right, to make it aromatic. So because of those, it does not follow the aromaticity rules, okay? And then now let's look at this, where it's also the same thing as this, but this one has just moved up a little bit, right? So we know, like, from the start, it's not aromatic because it doesn't satisfy the 4n plus 2, right? It has 2 pi bonds, right? 1, 2, which means it has 4 pi electrons. So it cannot happen. Remember, n has to be a whole number. I can't put 1/2 there, which makes it 4, but 1/2 is not a whole number, therefore I can't do that, okay? But also, it's also missing some of the other properties too, like sp2, this is sp2, while this one is sp3, right? This one is also sp3, sp2, sp2, right? But it's also missing that conjugativity, if that's a word. This pi bond here, if it's a conjugate, it should go here, right? And then one more, it should go like that. But it's missing this bond right here. So therefore, it's not conjugate. Um, all of the atoms are not involved in a double bond, and you don't satisfy this Huckel's rule, okay? So let's look at this one. Okay, you already know from the start that this isn't aromatic because it doesn't satisfy 4n plus 2, right? Like, um, uh, it only has 4, so it can't do that. This is sp2, 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 and this is sp3. So it's not in the same plane, and there's no double bond going up here, okay? But let's say it does have that cation. So what happens if it has that cation? Well, if it has that cation, it means that it's missing a an electron, right? So if it has that pi bond, I mean, um, if it has that cation, that means, well, there's no electrons here to help it create um, that aromaticity. It can't participate in double bonds where we have to go up here and then we have to do that, but it still doesn't satisfy the rule because we're still missing an electron, right? So if we do that, it's like this, but we also still have the positive here, and see how that's not really doing anything. It's just actually it's making it a bit worse because um one there's a starvation of electrons. You're unable to fulfill that aromaticity rule, and it's also a cation, which makes it very, very bad, a carbocation, right? So, and this doesn't satisfy for n plus 2, right? This molecule is not in the same plane, so this is not aromatic as well. But what if we add a lone pair of electrons to the mix? So if we add a lone pair of electrons, that means that this electron here has the ability to contribute double bonds into the system, right? So it can go here, while this one can go here, and this one can go to this, and then, or you can go the other way where you have it like this, and then this one goes here, and then this one goes here. But as you can see, it creates a system of, so now before you would have um, two pi bonds, but now this lone pair of electrons can contribute to aromaticity. So therefore, you don't have two pi bonds anymore. You now have three pi bonds. And with three pi bonds, there's 6 electrons, right? So if there's 6 electrons, you can fulfill this for n plus 2 equals 6 rule, where n is equal to 1, right? If n is equal to 1, then it would be 4 plus 6, 4 plus 2, which is 6, right? And these are all also um, sp2 hybridized. Try to convince yourself that these are all sp2 hybridized. But other than that, I mean, I think this is a very aromatic molecule. Let's see if we have a cyclobutane. Oh, I forgot to add this. Okay, if we have this, um, it's a cation right here. It doesn't look like um, it doesn't look like it can be aromatic, but because of the fact that we have resonance here, let me just show that real quick. Oops. Right there, and then the positive goes here, and then this can go back here, and then that means the positive is here, and then now this is here. You can see how in each scenario we have the double bond is shared within these three molecules, right? These three carbons. So the double bonds are within each other's carbons, right? And they are also all on the same plane. They're also sp2. And it also does satisfy Huckel's rule for n plus 2 equals, this one has 2. So if n is equal to 0, right, it has 1 pi and then another pi electron. So because of this, it does satisfy Huckel's rule, and this is aromatic, right? Whereas in this case, we couldn't make it aromatic because, well, one, even if there was residence here, it doesn't fit for n plus 2. And also just the fact that it's not conjugated, right? If it was conjugated, it would look a little bit different, and it would still not be aromatic because of this 4n plus 2 rule. Okay. And then, of course, we have benzene. Each and every carbon is participating in a pi bond. There's 6 pi electrons, so it fits a 4n plus 2. This is aromatic, right? This is our most favorite. And then next we have pyridine, which is a heterocycle. And a heterocycle means that it's a carbon cycle with another molecule attached to it that's not a carbon. In this case, we have a nitrogen, okay? So let's look. So nitrogen has electrons that may or may not participate in aromaticity. And how do we know that? So can these electrons participate in aromaticity? So let's see. So let's look at the conjugation of each carbon here, okay? And then let's also look at the conjugation um, of that nitrogen, okay? So this one is sp2, which is good. sp2, 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 sp2. And then you may think yourself that this is nitrogen is also sp2, right? So it looks good. It looks like it, oops, it looks like it follows. Let me just clear that real quick. It looks like it follows the planar rule that we have. How many electrons does it have? It has 1, 2, 3, 4, 5, 6, right? So it does have 4n plus 2. Is it conjugated? Yes, it does look conjugated right here. And this does fit Huckel's rule and everything like that. And this is an aromatic, right? But I want you to notice the difference between pyridine, right? The one that we just had here, and then Pyrrole. You see how this nitrogen had a double bond connected to it, and we didn't count this nitrogen's double bond, lone pair of electrons here, right? But with this molecule, there are no double bonds here connecting to this nitrogen, okay? So let's see. So this double bond can and will participate in aromaticity. So it goes like that, goes up here, and then this goes to that carbon. And if you take a look closely, um, each carbon is now involved in an sp2 hybridized, and there are also 1, 2, 3, 4, 5, 6 pi electrons because the lone pairs from this nitrogen is involved in making the molecule aromatic. So in this case, it is aromatic, right? We don't count the lone pairs if there is a double bond already connected to the nitrogen. We only count the lone pairs when there is no double bond connected to that element, okay? So let's take a look at this. You see how there's no double bond connecting it to this oxygen? So we would count these two lone pairs at the top here as pi electrons. And because of this, we have 1, 2, 3, 4, 5, 6. We have 6 pi electrons. Everything here is sp2 hybridized. This oxygen can and will be sp2 because, like I said, aromatic molecules are really stable. This is also aromatic. Okay. And then let's take a look at this. Again, same heterocycle. This is thiopene, furan, pyrrole, and pyridine. So these lone pairs are not, there's no double bonds connecting the sulfur. So that means these two double bonds are going to be participating in making this molecule a aromatic. So we have 1, 2, 3, 4, 5, 6. 4n plus 2, it fits that. N is equal to 1. And then we have sp2 hybridized on each and every atom here, including that sulfur. Okay, so let's take a closer look at this was Pyrrole here. 1, 2, 3, 4. Yeah, 5. This is Pyrrole here. So why are these why are those double bonds participating in aromaticity here? Okay, so let's draw this atom in a 3D conformation where you see that these are pi bonds here, right? But because this nitrogen has that double bond, it's also within the space of everything else in here, right? It's also a pi orbital. So that means it can and will resonate within these pi molecules here, and it'll form this cyclic, as you can see, where I'm connecting every blue in a circle, right? Like that. So because of that, it's in the same plane as those pi orbitals. The lone pairs are also in the same plane as the pi orbitals. So that means it will and it can participate in making the molecule aromatic. Okay. And then same thing here. So why is it in this case that these lone pairs are not they're not participating in aromaticity? Because there's this double bond connected to the nitrogen. Remember what I said? When there is a double bond connected to your element, we don't count any lone pairs that this element has, right? So this molecule is aromatic. So let's see that in a 3D conformation again. Again, we can make a full circle with the blues. Just means that these pi orbitals are arranged in a way that makes it aromatic, where it conjugates within one another and it's all within the plane of one another. But this lone pair, the reason why it doesn't participate in um, bonding with these other elements is that it's 90 degrees away from all these. This lone pair is not in the same plane, right? So that means because it's not in the same plane, it can't participate in making a molecule aromatic as this one. Because it has that double bond, it makes it so that the nitrogen already has a pi bond with it. Whereas in this case, because we didn't have a double bond connected to the nitrogen here had a lone pair on its pi orbital, which means it can still be in the same plane as all the other pi orbitals in the system. Okay. So now let's take a look at this. This is called cytosine. It's one of your sugars that you may come across in Chem 114A or B. So let's see if this molecule is aromatic. Okay. So first we can count these two because I think these are the easiest to count, right? This one and this one. Okay. So this is sp2, sp2. We have 2 pi electrons right now. If we go up here, this is also sp2. We have 3, 4. So not sp2. So we don't have 2 anymore. We have 4, right? 1, 2, 3, 4. Are these participating in aromaticity? They're not, because this nitrogen is already double bonded to this carbon, which means this is not in the plane of these molecules. Let's look at this carbon. This one is 1, 2. This one is also sp2. These double bonds are not participating because they're not in the same plane as these carbons here, which means these double bonds are only connected to this oxygen. Same thing with these lone pairs here. They're not inside the system. They're not within the system, right? So, and then do we count these 2 lone pairs here from nitrogen? We do count these 2 lone pairs in nitrogen. So we have 5, 6. So we have 6. Is this nitrogen sp2? Let's see. 1, 2, 3. Yes, it is sp2, which means that it satisfies every rule that we went over. Therefore, it is aromatic. Okay. I hope this was able to help, and I will see you on the next part where we are talking about electrophilic aromatic substitution.